Welcome, ladies and gentlemen. We hope you can see our pictures here well, and I as well hope that you can hear us well. Welcome to our Fiber Optics Fundamentals webinar concerning about basics of the fiber optic installation. My name is Thomas Hüsch. I'm a technical support and trainer here at Softing, and I would like to introduce to you Konstantin Hüdepohl, our product manager for Wire Expert and some other products. He is my co-moderator today, so welcome.
Hello, good afternoon, good morning, good evening, wherever you are in the world. I will be Thomas' co-pilot today. I will answer your questions in the chat. You can put questions into the chat anytime. We will collect all questions and put them and answer them at the end. Also in the sidebar, you will see some documents for download that will support Thomas' presentation today. And that's all. Have fun and see you later.
Thank you very much. So welcome to our presentation again, and short agenda today is who is Softing IT Networks, basic of light transmissions, fiber optic cables, fibers, connectors, then loss and faults of fiber optic links, fiber optic measurement, light source power meter, and Otdr. I'm a little bit in the way here. So and last point will be contamination of links and some further information for further webinars. Okay, let's go on. Who is Softing? Softing is a stock-held company, so we are publicly traded since the year 2000. It is a German company that was founded here in Germany in Haar in 1979. Our headquarters is in Haar near Munich in Germany, and it is a management holding run in accordance with the principles and values of a German medium-sized company. Medium-sized because we are, even if we are public traded since 2000, we are only 400 employees, and everything that is below 500 is a mid-sized company. We have an approximate turnover over the last year of 90 million euros, and we are locally represented in a lot of countries in this world, especially in Germany, Austria, France, Italy, Romania, USA, Singapore, Japan, India, and China. So we have a lot of locations where we are. The IT networks part is that part inside of the company, inside of the AG, that is for test and measurement equipment to verify, qualify, or certify copper and fiber optic infrastructure of IT systems. That is our part. We have a lot of products. So when you look here into our product list, we have the certifiers that are for traditional acceptance tests. We can test on copper as well as on fiber. We have the fiber expert, the Otdr. We have some qualifiers that are fairly new, and we can qualify data links on copper and on fiber up to 10 gigabit with that one. So a very nice product as well. We will talk about that later and again. The verifiers are the small parts, similar like the cable testers in copper. We have one small verifier that is the verifier that we can see here. That is a fiber optic verifier, and all the other stuff here is based on copper. Additionally to that product portfolio, we have a Wi-Fi network sniffer in place, the Wave Expert. That is a multi-channel, multi-MIMO capturing device that you may use when you are used to use Wireshark, and it can capture up to 4 channels simultaneously with 16 antennas in one housing. It is a very small housing. So this picture there reflects roughly the size compared to the other products. When we are looking to the Softing IT networks, we have some global offices. We have our headquarters in Munich. We have branch offices in London, Paris, Milan, and Vienna. That sounds more like a fashion company, but we are a technology company. Then we have a location in Singapore where we have an R&D, and in Shanghai a sales office. They serve the Asia Pacific room. We serve from Munich and our branch offices here, the EMEA room. And last but not least, in Knoxville, Tennessee, we have another office there that serves the American room, completely North and South America. Okay, that should be enough for that part here. We are looking into data trends. Data trends in the last year were always on a rising branch. So we can see that we are transmitting gigabit Ethernet, 10 gigabit Ethernet, 40 gigabit Ethernet as well. especially in the data center environment, but up to 10 gigabit Ethernet, we are still in the office area. So we need to make sure that this is all working well. And what we can see here, that it was an increase by approximately a decade every 5 to 7 years. So we are ending up today in 400 gigabit Ethernet over fiber in data centers, and that is not the end of this line. It will go higher in the future. Then let's look onto the generic cabling system. If we are looking to a campus area with several buildings, and these buildings usually are connected from the building distributors together to one primary campus distributor that may be seated in one building, but maybe as well somewhere else. So there is a primary connection between the buildings, and they are usually implemented in fiber optic. Up to a length of 300 meters, you can use multimode fiber. Up to a length of from 300 meter on, you should use then single mode to have the full capability of your network available. In the secondary area, that is the area between the floors, we name that as well backbone or riser area or vertical cabling area. You usually have the same multimode up to 300 meters. If you have to go higher than 300 meters, single mode. One addition to that one that is not part of the fiber presentation, but I can verbally tell that if you have between your building distributor in the bottom, that is down here, and your floors a distance that is less than 100 meters, then you can build up your backbone in a building as well on copper. But that is a rare variation in there. On the tertiary is the horizontal cabling, the floor cabling, that is usually implemented in copper, but you are allowed to have a second port on each work area as well with fiber. But there is a rule inside of our standards, in all standards, that says the first port must be fiber, copper, and the second may be copper then, or fiber. Then last but not least, one thing that is coming into that game as well is Wi-Fi. You very often have today Wi-Fi according to IEEE 802.11n with a maximum speed of 450 megabits per second. It is now extended to 600, and the new one is the IEEE 802.11ac standard that has a minimum requirement of 1.3 gigabit per second, 1.7 if you are having more than 3 streams, and 2.5, 5, and 10 gigabit will be necessary in the future as well. So make sure that your network can support these speeds and that you are capable of testing that as well. Usually Wi-Fi is connected via copper cabling. The reason for that is that you have power over Ethernet in place as well, so that you can support your access points with power. Today, mostly power over Ethernet plus, in some rare cases already plus, but the plus application is usually taken for something different, like lighting of the building. So that would be something that you would do with plus. Okay, that's enough for that one. There are some cabling specialties in there, specifically in ISO IC 11801 and EN 5173. You are allowed to have a decentral backbone. That means you have a building distributor on the bottom end here, and from this building distributor you can go with copper or fiber into the floors, and then you go out there with copper or with fiber or with both to the work area outlets. But that is a decentralized theory here, and if you are taking a centralized approach, you can take directly all your fiber links directly from your building distributor up into your floors, and that is then limited by the type of fiber. You are allowed here in this case to have multi-mode only, so 300 meter limit is there the case. The reason for that is that in horizontal cabling, you are not allowed to use single mode. The reason for that, again, is that single mode fibers have much too less attenuation for this application then. Let's look into the optical attenuation as a comparison. And this is a table that one of my colleagues has made very nicely, so I do not need to do that myself. When you're looking into attenuation per kilometer, and you look for Rhine water is the water of the river Rhine. It is more or less dirty because it comes from the Alps and brings a lot of stones and very small stones and sand and all this stuff with it. So the attenuation there is very high, 100,000 dB per kilometer. That means you have a drop in the power that is approximately after 3 centimeters, 3 dB, because 50% drop in power on fiber optic transmission means that you have a loss in there that is 3 dB. Then next one is a normal glass from Windows, has an attenuation of approximately 50,000 dB per kilometer, and that corresponds then to a 6 centimeter part of that one until you have a loss of 3 dB or 50%. Some people remember in former times when you had a cashier in banks, you could go there and cash your money out from there, and they had a very thick glass wall between you and the money. And then this was already looking a little bit darker and green in some cases, and that was the reason because of the high attenuation of this glass. Optical glass that we are using here to see better, that has still an attenuation of 3,000 kilometer per dB. So after 1 meter, if you would make a fiber out of that one, it would have a drop of 50% or 3 dB. That was not acceptable for fiber transmission. So the reason that we are today looking into different other stuffs is at the end, you look then into air that has an attenuation of 10 dB per kilometer, or you look into a good fiber in 1970 that had an attenuation of 20 dB per kilometer. You could already reach 150 meters with a 50% loss. Today, our multimode fibers have 3 dB per kilometer as a rough attenuation. There is a little bit more of an allowance in there. We talk about that one later as well. So looking into single mode fibers, we are at an attenuation of 0.4 dB per kilometer. That corresponds then to 7.5 kilometer of transmission reach, and that are the fibers that we usually use if we are doing transmission on single mode fibers in the campus area. So we would have enough power to go over a longer distance, but usually that is limited in the LAN environment to 1.5 kilometer. The last one is then the plastic optic fiber that has an attenuation of 100 dB per kilometer that corresponds then to 30 meters reach, and that is what is used sometimes in industrial environments. What we are now looking into is the electromagnetic spectrum. So we are talking about waves and we are talking about wavelengths. So let's compare some of those. We start with technical alternating current, and sorry for that, I missed to change that word technischer Wechselstrom into English, and we are looking into the low frequency area. Then we go into the high frequency area where we have our radio transmission. Then we go into microwave area where our microwaves are sending out signals, and the microwave signal is typically around 2.4 gigahertz. So that means as well, if you are planning a wireless LAN, you have to watch out for transmissions that are in this area, 2.4 gigahertz. So avoid microwaves or change the band, and you can go up into the 5 gigahertz band, and then a regular microwave doesn't interest you anymore. When we are going further into the microwave area, we come to frequencies of 1 terahertz, 10 terahertz, 100 terahertz, and further on, the next one would then be petahertz and etahertz and all this other stuff in the high frequency area. Usually you only talk there anymore about wavelengths. X-ray radiation is around 1 nanometer, 100 picometer is gamma radiation up to 1 picometer, and then it is getting really dangerous. So gamma radiation in that area is deadly for all human being and as well for not all insects. I have heard that some of those survive that. When we are now looking into our optic transmission, then we are in a small band area that starts in the frequency on a little bit higher than 100 terahertz, and we convert that into wavelengths in nanometers. And we start with visible wavelengths with 380 nanometers. That is the ultraviolet wavelengths. That is as well dangerous because it is already on the higher end where we are going into direction of X-ray and gamma radiation. Then we go down to the 780 nanometers. That is what you usually have as visible light. And a little bit of the visible light is here an example in my fiber lamp, and you can see that you have some light that is going out in the front here. These are plastic optic fibers that transmit the light in here as well already. And that is something that you can see. Beyond the part of 780 nanometers in the higher wavelengths area, we are going into the infrared area, and in infrared you cannot see anything. So the most important thing is never, never, never look into fibers if you don't know what is supported on the other end of the fiber. It may be a high power transmission for the metropolitan area networks or for the wide area networks, and in that area you can have power up to 2.5–3 watts, and then combined on a wavelength that you never ever can see in the very high frequency range in the third window, like 1550 nanometers and 1310 nanometers. That is something that we cannot detect with our eyes, and that can become really, really dangerous than if there is a high power source on the other end. In some rare cases in the wide area network, you find as well 1625 nanometers and 1490 in fiber to the home, but this is not the case for our LAN environment, so I take them out again. So make sure that you never look into any light source that is transmitting light in the multimode or single mode area if you don't know what is going on there. The next thing is then the attenuation of glass fiber specifically, was designed in the early 70s, and at that time we had still fibers in place with a so-called oxygen and hydrate ions, and these ions had made then some bumps into this attenuation line that starts at the low frequency range and goes then up to here on the on the low wavelength base and goes to the high wavelength bases here. And what was defined at the times was then the 3 different bands. The band number 1 is the band at 850 nanometers with an attenuation roughly between 2 and 3 dB on a perfectly clear fiber, and the band of window number 2 with 1300 nanometers and 1310 nanometers that was at that time used then as well for transmission over greater distances because the attenuation is here fairly low. And the 1550 nanometers as well, that goes more deeper here in this attenuation area. 1600 is still in place there for transmission of test signals. But basically, today we have fibers that are in the wide area network dried for these bumps that you had in there from the oxygen hydrogen ions. So today fibers can go up down to attenuations in this area that go down to 0.1 dB per kilometer. That would mean if you transmit signals, you would have then a transmission loss on that one that is for a 100 kilometer long link, only 10 dB. And 10 dB is something that we can still recover with amplifiers, and then we have the chance to amplify that as well. That means if you're looking into transcontinental fiber links, these are not powered with a kilowatt source on one side and they come on the other side with 0 dBm. They usually have attenuation in there every 100 kilometer of 10 dB, and then they have an amplifier built into this cable. And these cables, amplifiers must be supported by power as well, and that becomes then a little bit more critical. So you will have a lot of amplifiers in such a transcontinental link, but we are only looking into the LAN environment. Let's go for optical fiber cables. You have outdoor cables, you have indoor cables, and these are usually connected to connectors with so-called pigtails, and they are spliced on that. And additionally to that one, if you want to run a distance that is more than, let's say, roughly 10 kilometers, your cable drums become a little bit thicker. For an outdoor cable that you can see in that picture over there, is only with some fibers. You have today outdoor cables that are from my upper arm, from the size of the upper arm in the outside diameter, with protection against humidity, with a protection against animals that try to bite into that one as well. That is more important as you may believe. And when you change from an outdoor cable to an indoor cable, you can splice them directly together if the core diameters are the same. If not, you have to put an active component in between. If you are looking into the LAN environment, then you will have more or less breakout cables that have the ability to be connected directly to a connector. So you can glue the connectors onto that one. And that is as well a common practice if you are looking for pre-terminated cables. Pre-terminated cables will have then a bunch of connectors already connected, and then you have a pull loop on the ends that you can pull these cables into your installation as well. Okay, let's look into fiber optic cores. You have on a loose tube, this is the name of the small tubes that you could see, sorry, on the picture before, these small tubes that you have here. In these tubes, normally in an outdoor cable, you will find as well a jail in there. And we had that as well in former installations on the indoor cables. And that was a problem sometimes, because when you pull a cable then into the vertical, then this jail tries to drop out on the bottom side, and it floated sometimes some patch panels, and that was not very good. So today you will find loose tube filled with jail only in the outdoor cables, loose tube unfilled. In the indoor cables, you have compact tube fibers that have an outer diameter of 900 micron, or a solid filled tube. That one is on the higher risk that you cannot get the outside protection coating away from your fibers. So usually the compact tube is that what we are using today in our LAN environment. Okay, that should be enough for that one. The fiber structure itself is today a fiber coating that you have around your fiber. Inside you have the coated glass that is a cladding, and that is the core of the transmission, not perfectly, but it is a part of the transmission already. And inside you have then your core with different diameters. You have a 9 micron diameter on single mode fibers, you have 50 micron diameter on multimode. That is the most common used diameter on multimode fibers at all. And you have 62.5 microns in old installations. That was an OM1 fiber. But basically, the important part in here is that you need a core, and inside of this core, the light signal is transmitted. The cladding around that one is made as well out of glass, and is different on the different types of fiber that you have. On a single mode fiber, because of you want to have a low insertion loss, you will have a perfectly clear core, and the cladding outside is then with some ingredients in there that you get reflections in there. And on the multimode fibers is a straight way, opposite way around. Okay, let's look into POF as well, plastic optic fibers. They have 100,000 microns outside diameter. The factors that affect the propagation of light is especially if you are looking from different medias. And the picture that you can see there, I have it here as well as a live demonstration. You can see in a glass, if you put 2 sticks in there, that there is something different. And that is a part of the refraction that you have on fibers. And the refraction on the fibers, that is one of the things that we are using as well in the total transmission of our fibers today. The reflection happens if you don't have perfectly connected fibers, or if you have a connection that is not perfect, then you have an angle in there. The angle is depending on the fiber index. The fiber index is named N, and this fiber index makes then a difference how the signals travels into the different media, and the density of the media as well is a lot of importance as well. Then we are looking into optical attenuation on different types of fibers. You have the optical attenuation for optical multimode fibers, optical single mode fibers. The optical multimode fibers 1 and 2 that are orange here in this place, these both are grandfathered in between. They are not anymore part of the standards. They are in the attachments of the standards. The OM3 fibers, that was the first fiber that came into the market for transmission of multimode signals over a little bit distance, and as well additionally over high speeds. And to get to this OM3 fibers that happened in the let's say in the end of the 90s, you had the first OM3 fibers out there, and the speciality is that you have not only one core that is dotted inside of this fiber, you have up to more than 1,000 different rings inside the fiber that are differently dotted, and that brings the capacity of these fibers up to speed. So that is one of the main features today when you're looking into OM3, OM4, OM5 fibers. They have as well a color designation. An OM3 fiber as a pitch code should be in aqua. OM4 should be in, I don't know what this color is named. I think that was some flower's name. I can't remember that, but it's violet. And the OM5 fiber is this lime green. On single mode fibers, you usually have, when you are having patch cords, you usually have then the coating outside in yellow, but it is not something that is written into stone. It could have another color as well and have different approaches inside there as well. Plastic fibers have something like a rose color, but these are usually only used in very short transmission links, like the toss link fibers that you find between your TV or receiver and an amplifier. There you can find these things as well. The corresponding smallest modal bandwidth has improved a lot over the time. And when you see that the bandwidth of an OM1 fiber was 200 megahertz multiplied by kilometer on 850 nanometers, and that is the transmission frequency that we use on multimode, then you could see that you could reach up to 1 gigabit for 200 meters. And on optical multimode fiber 2, you could already reach up to probably 500 meters. And the speed goes up with the OM fibers 3, 4, and 5 up to today, up to 4,700 megahertz multiplied by kilometers. So you can run approximately link lengths there with 300 meters well to transmit the 10 gigabit over one pair of fibers. The single mode fibers do not have a limitation in capacity. That is only depending how much signal you get out of a transmitter and into this 9 micron fiber. And there you can see in the LAN area attenuations of an OS1 fiber. It is in between named OS1A. Sorry for that mistake. And that has a 1 dB per kilometer, so that is really fairly low. And you can go for an OS2 fiber in the outdoor environment, but you don't need to go to the wide area fiber with 0.1 dB. That does not make any sense in the LAN area because your length is already limited to a length of 1.5 kilometer. Then there are some special things now today with the multimode fibers, specifically on the OM5 fiber, and I have to go out of the picture here. They do in between today as well wavelengths division multiplexing between 850 nanometers up to 953 nanometers. For that will mean that you will have the ability to put in there different wavelengths in a coarse wavelengths division multiplexing, and then you can put up to 40 gigabits, or if you put each time 25 gigabits into the fiber, up to 100 gigabit over one single multimode fiber. And that is normally used then in data centers where you need really this high speed. Okay, let's look into the structure of a fiber optic connector. This sample is of an SC connector, and as well, I apologize that I did not translate the Stecker over there. And there is a housing around this, and the housing is on a size of several millimeters in roughly a square. And there is as well a ferrule in there. This ferrule has 2.5 millimeters. Inside of this ferrule, then there is a fiber glued in there, including the cladding, the cladding of the fiber core itself. That is on a diameter of 125 microns, and this hole that is inside of this connector to glue it in there is 126 micrometer. So it is a very tight stuff thing there as well. When you are looking now for different types of fiber optic connectors and the typical insertion loss, you can find there that there are some specific rules in there. Physical contact connectors, in example, have a normal regular physical contact. They have an return loss of better than -20 dB, and the angled physical contacts connectors have -65 dB, and super physical contacts, there is something that is better polished on the surface, will have then -40, and ultra polished -50. That is depending much on how much power you want to transmit over these links. If you are using the regular powers like around 1 milliwatt, then it's probably not often necessary to have an angled physical contact connector, because the power that is returned then is not too much to kill your transmitter. On wide area networks, there were some really specific things in there. An example, on the Opal network of the German Telekom, they have developed from one specific company the E2000 connector here that has a very, very low loss on both multimode and single mode fibers, and that was designed as an angled connector in the first time. So it is today sometimes the case that some people install E2000 connectors in LAN environment, what is unnecessary expensive, because one of these connectors costs you around 20 euros or sometimes more, and these are really difficult to build. So the main connectors today in place is the SC connector from older installations. FC is normally used more or less most on test equipment, and the LC connector, that is something that you will find today on most of the active equipments. The LC connector is a connector that has a footprint of a probably roughly RJ45 size, so that makes really sense to have such a small connector in place. Okay, intrinsic coupling losses. That is when you lose light. Usually that is something that can happen to you. In example, if you have different core diameters. That is more important in the outdoor environment if you're looking into wide area networks, where you may have sometimes when you have a splice done between two different fibers, that if the core diameters are not perfectly matched, then you may have not a loss in this connection. Then it may happen that you have then a raise in the amplification area, and that is not possible on fiber. You always lose something when you are going through a splice, but the measurement technology shows it as it would be an amplification in there. So different core diameters or possibly form variation is a problem. On multimode fibers, usually if you have 50 microns, if that varies about ±1 micron, it doesn't matter that much. But on wide area networks, it is very important to have a real tight, close to each other core diameter to have a perfect match between these fibers. So different refractive index profiles, like a step size profile and a gradient profile, that would not match each other as well. So be sure if you have a connection between two fibers that you have the correct refractive index profile that is running on there, and we can then probably have problems if you don't watch that. Then we have some extrinsic coupling losses. Coupling loss is usually something that you have then if you put fibers together with connectors. And if you have a space in between there that is more than in a nanometer area, then you will get a problem there about coupling loss. If you have a radial offset, so a wrong coupler, or you have spliced the fibers together in the wrong way, then you will have a radial offset in there, and then you will have a higher attenuation as well. And if you have a tilt angle error in there, that can be as well a problem, specifically if you have a plug and coupler combination in there. It may be a faulty plug or a faulty coupler then, and that can cause then real serious problems. There is one connector out in the world that is the Mtrg connector. If you hang an Mtrg cord from a patch panel straight down and you don't fix it in holdings for the fibers, for the cables, then you may have a problem there that you can then get a tilt angle error. So make sure that this is working fine. Konstantin, kannst du das Bild wieder da ausblenden? Entschuldigung. Danke. Additionally to that one, we now have some other things in place, like in example, end phase roughness or dirt. If you have dirt between two connectors, or if you are having dirt between two fibers that you want to splice together, you will get a problem. A different angle, if you put different connector types like an UPC and an APC connector together, or a PC connector and an angled connector together, then you may run into really problems as well. You get this very high reflection there, and that and additionally a very high loss then. And you have, by reflection loss that happens on the surfaces of connectors between these two connectors that you have put together, you may have then as well a reflection loss. Then parameter groups. What must be measured according to ISO IC 11801 and EN 5173? There is a scheme in there that tells us what we have to test. On copper, you have a lot of transmission parameters that we have to test. That was a part of our presentation yesterday. Who missed that presentation? We have recorded that one and it's available shortly as well on our website, and all that have been there will be getting this video automatically. On fiber optic, you only have 2 fibers in a transmission. Typically on the LAN environment, on wide area networks, you can have as well transmission on 1 fiber in both directions. But in the LAN environment, you always have 1 transmission fiber and 1 receive fiber. And what is most important there is the polarity. Additionally to the internal transmission parameters, you have attenuation and lengths in there for the runtime or the delay of these fibers. So there is something as well interesting. Length is in our cabling standards from ISO IC and EN 5173 not a parameter that is a pass and fail parameter in there. This is only only in the TIA, in the ANSI TIA 568 standard. There is length still a pass and fail criteria. So when you're looking into what we are doing here, we basically don't have a lot of these things here in fiber. We only have continuity, and that can be tested, an example, with a very easy product from us, and that is a visual fault locator. And a visual fault locator is an optical light source that radiates out red light. And you can see that this one here is a fairly powerful radiator. If I would send it directly into the camera, it will overflow the camera fairly well. And this one is a light source that you can use to see if your continuity and the polarity of your fibers is working properly. So that is something that we have to do. We have to check for the polarity. Then we have to check for attenuation. And length is an optional parameter that you may measure, but you can as well go and read it from the marking of the cable. That is written exactly in that way in the standard. So basically what you have in there is the ability to do a verification testing inspection with a light source. Visual fault locator, VFL, is a short name of these things, and the visual fault locator is that part that we use when we are looking into continuity, and as well if we are looking into polarity things. On the qualification, you are looking into the determination of transmission performance of data links. We had that yesterday for copper as well. So you can look into the speeds of 1 gigabit and 2.5 and 5 and 10 gigabit on copper. And on fiber, you only can look into 1 and 10 gigabit because there are no transmitters available for 2.5 gigabit and 5 gigabit. That is something that came into this market only for copper transmission. So that is as well a possibility to look if your link is transmitting well in fiber optics as well, your 1 gigabit or 10 gigabit speed, both running at 850 nanometers. So basically what this tester is doing then, it is determining the transmission performance of data links with real SFPs, the small form factor pluggables. And at the end then we are looking into the certification. And when you're looking about certification, you may have the wire expert in place with fiber adapters that you can use there for attenuation measurement and length measurement. These adapters as well determine the length of a link, because they then calculate the limit performance for this fiber link that you usually have to do on your own, and compares it then with the values that are measured. So we can do a certification based on the standards that we have inside as well this instrument. The next one certifying instrument would be then the fiber optic OTDR. So an OTDR is an optical time domain reflectometer that measures backscatter and reflection measurements. And because it measures the times as well, you can then as well find out where you have your reflections and where you have your attenuations. And it can evaluate these as well against limits. So you would be able to see on this instrument as well if you have a passing or failing link. Okay, Lightwave is a new way of fiber optic loss determination that is built into our NetExpert XG, and we were the first worldwide who put that into such an instrument. We can measure the optical transmission loss between the SFPs of the units, and you need 2 of these units for that one. And you can then check how the attenuation varies over time when you start to wobble onto connectors, in example. And additionally to that one, you have a lot of other functions built in there, like as well the determination of the optical transmission loss, the length determination. You can as well evaluate the fiber, the connector end faces with a microscope. So that is coming now to an attenuation measurement. When we do attenuation measurements, and this sample here is for a 2-jumper reference, we talk always about reference setting. Reference setting is very much important because you have a light source that should be stable, and you have a receiver who should know what the light source as a power sends out. To do that, you connect these both together with a coupler on a 2-jumper reference. If you have a 1-jumper reference, we talk about that one later again. Then you plug your first cord that is coming out from your light source directly into your power meter, and then you can do a 1-cord set reference. The light source is then not only then switched on, it should be switched on 15 minutes before you do the set reference, because a light source must be stabilized, and a stabilized light source means it should have warmed up. And specifically on our instruments, on the wire experts, there is as well written into the handbooks, please wait until 15 minutes heat up time of your light source is settled, because they may drift if you don't do that. If you do a light source switch on and directly connect it to your power meter and set reference, then the set reference may be different in 15 minutes, and you don't want to do that. Once, if you have done the set reference by switching on the power meter and measuring the power, then you can set that to 0 dB. On modern instruments, you can do that in 1 set reference process for 2 wavelengths. And if we are looking into the wire expert, then you can do it for 2 fibers additionally to that one. So we can set reference for 2 fibers in both directions in the same set reference process. After that, you then put your coupler in between away, put a cabling under test in there, and then you can measure the insertion loss of this cable under test. And that is the reason that we very often talk about insertion loss measurement if we are talking about fibers, because we put a load, let's say load in between here, that reduces the amount of light that is from one side that you have referenced to the other side that you have your power meter on there. And if you're looking into that one, you will then get the results there for the different wavelengths, for as well the 2 fibers if you have done it with a wire expert with 2 fibers set reference, and you can get it as well in the reverse direction with the wire experts. There's a process built in that you then swap the connectors on the patch panel, and then you will be able to have the direction reversal in the fibers to measure them. One very important thing is, once you have plugged in your fiber into your light source, this is the holy cow. Never unplug this connector here before you have done all your measurements, because if you unplug this connector, then you have to do set reference once more. That is as well ruled down into our standardization papers. So let's look into single jumper reference. Is only 1 reference cord used, and you use a receive cord, and you ignore that there is a small amount of attenuation between the reference connector on the transmitter side and the reference connector on the receiver side. The 2-jumper reference is usually used if you don't have the ability to plug your correct connector that you need on this end to connect to your link under test directly into your power meter. Then you can do a 2-jumper reference, or you can go for the 3-jumper reference that is recommended today from the standards. that has then 3 reference cords between the light source and the power meter, with 1 cord in the middle that is only maximum of 10 meters long with 2 reference connectors, and that can be used as well for patch cord testing, or if you have different connectors on the link under test on both sides. And then in that case, these both connectors are referenced out on both sides as well. So these are the 3 different types in a short form, and on another presentation we will do for sure it in a longer form and explain much more how you do that. If you're looking into an OTDR, optical time domain reflectometer, then you have a controller that brings out pulses. And the controller then sends these pulses to an optical source. That one sends the pulses then to a splitter, and this splitter sends the signals out into the fiber. If you do that, you will then be able to have a signal into your fiber under test. Then the signal from your fiber under test returns back, goes through the splitter, goes into the receiver, and it is a directional splitter in there. So that power that is coming from the optical source is not directly led into the receiver, then it will blind this thing very much heavily. And so basically there is a directional splitter in there that sends the signal out from the optical source into the fiber, and from the fiber everything that is coming back inside of the splitter then will be turned into the receiver. There's usually then a photodiode in there with a very, very high sensitivity, so that can measure then the backscatter of the fiber in total. So that is basically what an OTDR is, a functional principle of that one. How much intelligence you build into this controller in here, that is depending on different manufacturers. So if you have a good manufacturer who puts in a lot of intelligence into this controller, so you may have an instrument that is quite good to be used in the field. Okay, what does an OTDR measure? It can measure distances and lengths, the total length of a link, the distances to events like breaks or connectors. It can measure point-to-point distances by putting some cursors in there. You can put the cursors on every position inside of your link, and you can set usually in the most instruments 2 cursors in there, and then you can measure the distance between the events that you have in there. You can measure the attenuation of a fiber. That is usually the angle with which the attenuation line goes down here. Additionally to that one, you can measure the attenuation of splices by measuring before the power level and behind the splice power level. The same applies to connectors. If you have a connector in there, you measure before the connector and behind the connector. There are a lot of sophisticated ways how to do that properly, and that is what we can measure. And you can measure microbands, macrobands on single mode links, because single mode fibers are usually very sensitive to bending. And if you do that in the wrong way, then you will have a loss in there. You will have a micro or macro band in there that will then bring out your signal to the other side on a lower level. The connector quality for return loss and anomalies on the link by reflection can be seen as well. Okay. Inspect before you connect is one of the important things that we always have when we are looking into fiber optic connections. You need to know what your fiber optic connection is all about, and inspect before connect means you have to look to the surface of your connector, to the end face is a correct name for that one. You can do that with optical microscopes, but if you have a cheap one without an infrared filter built in, it could be a little bit dangerous. So don't take a direct view microscope. We have the ability to put the microscopes that you have here in place to all of our instruments, to the fiber expert, to the wire expert, and as well to the net expert. And there you can evaluate from the standard IEC 61300-3-5 or 3. You can define exactly how much dirt is still allowed here in these areas, in the core area, in the cladding area, in the glue ring area, and in the contact area that is 250 microns wide. That is something that you don't see with your bare eyes. So make sure that you have a possibility to check for cleanliness of your connections. If this is not in place, then you may have a problem. So the real critical part on a connection is always the physical contact between your 2 fibers. This one here must be very, very clean. If that is not clean, then you may run into a problem. And there are the three basic principles of a perfect fiber optic connection. The perfect core alignment, that means that everything that you put in there, that the cores are set to the proper core centers. And if that works fine and you have no physical uncleanness in between there, then it will work very well. So a physical clean contact, a direct connection, and the perfect core alignment, that is something that you want to have. If you may have dirt in between in there, if you have a contamination in your connection, then you may have a real significant problem by reflections that happen there, because of the reflection, a higher attenuation, and possibly as well a damage that can happen there. So visual inspection of the fiber optic connectors is the only safe way to make sure that these end faces are really clean. So check for contamination before you plug in, because if you don't watch that, it may have at the end a physical damage then. Here are some miscellaneous contamination pictures, like single mode and multi-mode. Okay, should look similar like that. If you have dirt or particles on top of that one, if you have finger oil prints or fingerprints on there, or oil on that one, if you have scratches on there, if you have cleaner residuals on that one, so the alcohol with which you usually do the cleaning of this fiber, that should be as well not in place there. And you may have as well some glue resists rests on here. So this here would be a connector that would never ever pass, similar to that one. So all these connectors that has some dirt here may not pass a test, but the first and the second one, they will probably pass. So cleaning for connector end faces can be done by dry cleaners. There is a wide range of dry cleaners available in the world. You can do it as well with alcohol and with lint-free fibers, so that you don't put any contamination from your tissue that you are using onto that one. Never ever try to clean a connector by wiping it on your clothes. That will damage a connector perfectly. Okay, so cleaning can be done in different ways with different stuff that you can use. You can use as well fiber wash pens. You can have these lint-free tissues as well here on a roll. There are so many different ways, but the most important is make sure that it is clean. Last but not least, a little bit of marketing now. We have a marketing action out in there. Our promotion is valid until end of May. Conquer the fiber optics world. That is our spring promotion. We named that one because it is started in spring. We don't still have spring outside. We have still rain outside, but different issue. And in that one, you will find a lot of stuff in here. Not only fiber optic stuff, you as well will find a lot of stuff in there, like the copper wire experts, an example as well, to a fairly reduced price. And make sure that you have a microscope that you want to have if you want to have a clean surface on your connectors. One of the other things is we have done an online seminar yesterday, and that was about copper fundamentals. We have done today the fiber fundamentals, and we will have cabling standards next week, Tuesday. That will be Konstantin Hüdepol himself, who is sitting here beside me, and he will do the cabling standards update next week. So make sure that you grab your seats for that one as well. That's all for the moment. Thank you very much for your attention. And if you may have more questions, please feel free to ask. We will still be here for 1 or 2 minutes. And if we are already gone from the presentation, here is my email address. You can always drop me a notice to my thomas.hüsch@softing.com, and I will try to answer your questions as soon as possible. Thank you very much for your attention. Now the questions.
Yeah,
Konstantin.
Hi. We had a few questions. One was, when do you choose a power meter light source, and when do you choose an Otdr? Is there a rule of thumb, or?
No, that is clearly defined in the standards. The tier 1 certification should be done with a light source and power meter, and the tier 2, if you are looking for faulty links, must do with an Otdr then. So basically tier 1 is light source power meter, and tier 2 is light source power meter and Otdr measurements. That was based on the theory that an Otdr cannot certify. Today you can do as well OTDR measurements with certification, so you don't need the light source power meter anymore for a tier 2 test then.
Okay.
And it is allowed from the standards.
All right. And second question was, if you do a 3-jumper method, why do you need the middle jumper?
Because if you have different connectors on both sides of your link, let's say you have an SC connector in the distribution room, and you, or different way, other way around, you have an LC connector on your panel in the distribution room, and you have an SC connector because it's more handsome for the users. Then you have different connectors on your link. How do you want to get your reference cords together to check that? Right. And that is the reason that you are using then 3 cords, and the middle cord has then on one side an SC and the other side, other way around, on one side the LC connector, on the other side an SC connector, or whatever type is used anyway there in the installation. Then so different connector types between the patch panel and the wall outlet at the user should have then the 3 jumper set reference in place.
Okay, so but when the connectors are the same on both sides, we would always recommend the 1 jumper.
Yes, so 1 jumper is the most easy and most precise measurement that you can do. The reason for that is that you only have to calculate at the end what the reference to regular connector brings you as an attenuation into that game, and that is the reason that you have the 1 jumper as a very much preferred method of the standards. The standards always say, if you can do that with a 1 jumper method, do it. If you can't do it with a 1 jumper, then take the 2 or 3 jumper method. And in some of the international standards, it is allowed to have a 2 jumper reference. In some of the local standards and the European standards is not allowed. There is a difference between the standards as well.
Last question was, you also mentioned plastic optical fibers. Does it make also sense to test plastic optical fibers?
Basically, you don't need to test it. If you have the visual fault locator and the light receives on the opposite end, it is usually enough power there for this low speed transmissions that you are doing there. So that should not be a real problem that you need to test it.
Okay, cool. That's all. I'll have a last glance on my screen here.
Yeah. Anything else?
We get more questions.
Okay.
One more question.
Okay.
What was that? What about different multimode types?
If you are mixing up 62.5 and 50 micron, you get a higher loss in there. That is one of the biggest problems. If you are mixing OM3, OM4, OM5, yes, the refractive index of OM3, OM4, and OM5 is a little bit different. So you should make sure that you have at least an OM3 fiber, that if you're going onto links with OM4 and OM5, but the best way would be to have the same reference cord as the installation cable you have there. So if you have an OM5 installation, you should have reference cords with OM5 as well, but it is not that critical. More critical is the difference between the speeds on these fibers. So if you want to have a high-speed link, take more the OM3, 4, and 5, prefer it than the 5 one. And if you have a low-speed link, you can go down to OM1, OM2, but they are, as I told before, already grandfathered in the standards and put into the attachment. So these fibers will die out in over shorter length.
Okay, thank you.
Okay.
That was all of the questions.
Thank you very much. Again, thank you very much for your attention. And if you have much more to ask, feel free to drop us an email. That is not a problem at all. Thank you very much for your attention. Bye-bye.
See you.